So normally in a DC machine, we have what? We have field system, we have armature, and a field system consists of several number of poles. In each poles, we have, if you see this figure, in each pole, we are going to wound the shunt field winding. Along with shunt field winding, we are going to wound even the series field winding. Okay, the winding done around your pole, it may be a square pole or it may be a round pole. There are two types of winding. It will be a shunt field winding, normally at the upper part, and lower part there will be a series field winding. And a shunt field winding will accommodate almost 80%, and a series field winding will accommodate almost 20% of the portion. Okay. Now, pole design. The design of poles involved in the determination of area of cross-section of poles and their height and design of field windings. So here I am not going to design anything about pole. We are just concentrated on design of a field system. Okay. Area of pole, the most usual form of pole is a lamination type with bolted to the frame. You can see here, there will be several lamination of pole. Okay, this is almost a square pole or a rectangular pole. Each lamination will be insulated and it will be bolted. You can see here there are around 6 bolts. Here 4 and here 2 bolted. The pole lamination may be relatively thick of 1 mm to 1.5 mm, and stacking factor may be taken as 0.95. Stacking factor means nothing but the insulation part. You can take, but stacking factor is nothing but the net iron part. You can take 0.95. Another 0.5 is low for what? Go for insulation. Okay. The main pole carries total flux per pole and useful flux plus a leakage flux. So normally, whatever the flux are produced by the pole is nothing but your main flux. Along with once again, this can be have some leakage flux in the poles, because nothing but we are going to own the winding. Always there will be some leakage reactance and there will be a leakage flux. Along with that, we will have some useful flux. Okay. Now, leakage coefficient, or what will be the leakage flux? Nothing but what? Total flux per pole divided by useful flux per pole. So whatever the total flux divided by useful flux, and what you get, you'll get the leakage coefficient, or what you get, you can get the leakage flux. Or total flux per pole is equal to what? Leakage coefficient into useful flux per pole. So flux per pole 5P is equal to what? C1 into 5, where leakage coefficient is nothing but C1 and 5 is something but useful flux per pole. The flux density in the pole body can be assumed to lies between 1.2 to 1.7 Weber per meter square for laminated poles. This is the standard values. The flux density in the pole body lies between 1.2 to 1.7 Weber per meter square. This is regarding what? A little bit information regarding the pole and what should be the flux density around the pole body. But we are interested with what? Interested with the design of field winding. So you can say, if you see this figure, this is something but your pole, and you have a pole core laminations, and what you have, so you can see here, this is something what we call as what? Shunt field winding. Here I not show the series field winding. If you see this cut section front view, you can see this part is shunt field and this part is your series field. So exactly what we are going to design here in shunt field means, you have to find out what? You have to find out the length of meter. Okay, length of meter. And you have to find out the height of the field winding, and depth of the field winding, and what is the current carrying in the field winding, what is the loss dissipated in the field winding. All those parameters we have to find out, and number of turns of the field winding. These are the things we are going to find out in the field design. Okay. In shunt machines, the entire winding space along the height of the pole is taken up by the winding, while in the compound machine, 80% of winding space is taken up by shunt field, and rest of 20% by the series field, as I told earlier. Okay. This is something but what? If you see the winding, if you see the winding, is something about height. This is something about depth. Depth is nothing but the thickness of winding. And if you cut this section, you can see here. You can see the winding section here. So normally at the top it will be shunt, and the bottom it will be series field winding. Okay. Along with that, so the entire length. For entire pole length, the winding will be not done. Only for a certain portion, the winding of a shunt field or series field will be done. Okay. This. Now design procedure. Assume suitable depth DF for the winding. So one by one, I'm going to tell. Listen carefully. I'll go slowly only. Listen carefully. assume suitable depth of the shunt field winding. Okay, assume suitable depth df for the winding. Df is depth. Depth is nothing but what? Your thickness. You're going to own number of turns. Like that, what you get will get the thickness. Depth is something also called as a thickness of your field winding. Okay, that is first step. Calculate the length of minter and length of minter. This means you have to calculate length of minter. Length of minter means this one. Length of minter. This is your inner turn of your field winding. So first there will be a pole. This is nothing but your square pole. The pole body will be square. After the pole body there will be some insulation. After that you will have a inner turn of your field winding, and this will be a outer turn of your field winding. And this is called as what? This is called as your thickness. So length of meter means I have to calculate length of meter. Length of meter means I have to take consideration into the length of meter of inner turn, that is nothing but Li, a length of outer turn of a field winding. But what I want length of meter means I want to take what? I want to take the average of for Li is nothing but the length of meter of inner turn, and this is nothing but the length of meter of outer turn. So length of meter of winding means then I have to take the average between these two, because the length of meter will not be same for innermost winding. This will be the length of meter, but outermost turn little bit it will be more. So that I have to take it average. So what I do means I will divide by what? Li plus L naught divided by 2. I take the average. In between value I am going to take it. Calculate length of meter. The length of meter is, so if you see here, this is something but the winding done on the square pole or a rectangular pole. Okay, length of meter. See LMT. See you can see here, this is your what? Length of pole body. This is length of pole body, and this is a width of pole body. This is something but your top view. If you, I'm saying I go back to the figure. This is you see from top view. This is and this will be the figure. What I'm going to show here. Nothing but top view. So this will be what? Length of a pole body. And this is your width of pole body. What I shown in dark here, nothing but insulation. After this insulation, what you got? You got the Li, nothing but what? Length of meter of inner turn of your field winding, and L naught is nothing but the outer turn of your field winding. So you have to take what? In between value, you have to take it. In between value means what I shown in the dotted line. So length of meter means you're going to consider this dotted line. In between means exactly half between the inner turn and the outer turn. This is called as a length of meter, and what I showed A, B, C, D, E, F. Okay, small letters. So length of meter, what you can calculate now? Length of meter is nothing but what? A, B, C, D, E, F, E, F, and G, H. That will be your length of meter. Let us calculate now. Length of meter is equal to what? 2 into LP. LP means something but what? Length of the pole. Length of the pole means this will be length of the pole. How much? This side one length and this side one length. So 2 LP. Likewise BP, nothing but width of the pole. This side one width of the pole and this side one width of the pole. 2 into BP plus 2 into DF. DF is nothing but what? Your depth of the thickness of the winding. Here one DF, here one DF, and here one DF. Okay, that will be your depth of the winding. Once again, I am showing this figure. It is clear for you. Say depth. Here one DF, here one DF, 2 DF. Then two side length of the pole. Length of the pole means here one length of the pole, here one length of the pole, and depth is nothing PP, nothing but your depth of the pole. Here one and here one. So you're going to take what? The here lengthwise 2 times, depthwise 2 times, depth or width, and depth of your field winding is DF. Okay. BP is nothing but width of the pole, LP is nothing but length of the pole, DF is nothing but your thickness or depth of field winding. So length of meter you can take what? 2 times LP plus BP plus 2 times DF. Okay. Or this is one formula is available. Or you can take L0 plus Li divided by 2. As I told earlier, this will inner turn will be Li, length of meter, inner turn of the field winding, and this is the outer turn, means capital PQ, SW, X, Y, Z. This is the outer turn. So you have to take average. So Li plus L0 divided by 2. So L0 plus Li divided by 2. Then what you get? You get the length of meter, means this average value you get. In between average value you are going to get it. So based on the data given the problem, either I can use for this formula, or I can use this formula. Okay, based on the data given in the problem. This is the formula regarding to find out the length of meter of your field winding. Let us come for third step. Let V be the rated voltage. Assume that 50 to 20% of rated voltage is lost across the field regulator. Therefore, voltage across the shunt field winding. So normally, if you're going to excite this field winding around 10 to 20% or 15 to 20%, there will be a power loss. Means there will be power loss. So only the 80 to 85% voltage will be available across the field winding. Okay, that is the meaning. So remaining 50% goes in a power loss, nothing but the drop across the shunt field winding. So what is EF? EF is nothing but the voltage. Voltage in the your shunt field winding, available voltage in the shunt field winding, means this is nothing but divided by P means what? Particular to a single pole. Okay, 0.80 plus 0.85 volt into P. So 0.80 to 0.85 V is nothing but whatever the voltage you're going to give to the field winding to excite the field winding, divided by P. P where P is the number of poles. Number of poles is equal to number of shunt field coils. So how many number of poles in the machine, that much number of your shunt field coils will be available. And all the shunt field coils are connected in series. So likewise, if you have number of poles, all the shunt field coils, suppose if you have 4 number of poles, and all the shunt field coils will be connected in series. Okay, after this wounding, once again it will be connected to another pole. Okay, all the shunt field windings will be connected in series. So we can say that the voltage available across the shunt field winding will be what? 0.8 to 0.88 times the applied voltage. Applied voltage then divided by P means for a one pole. Next, fourth part. Ratios of each field coil. RF is nothing but what? EF by I, same thing. Voltage by current. Where let AF is equal to cross section area of the shunt field winding. AF, small AF, is the cross section of shunt field winding. Cross section of shunt field winding. TF is equal to number of turns per coil. TF is equal to number of turns per coil. Number of turns per coil means number of turns with respect to one pole. Okay. The next AF. So AF, I can give the formula now. AF is nothing but what? Rho LM by LMT by RF. So similar to area. Area is equal to rho LMT by RF into TF. This is the formula. Okay. Next, rho LMTF. So RF, for RF you put this formula EF by IF, then what you get? EF, IF will go to the numerator. Okay. So AF is equal to rho LMT divided by RF into TF. Then I want RF. What is RF now? RF is equal to rho LMT TF divided by AF. That's the formula for what? Resistance of each field coil. Okay. Next, go for next step. Choose suitable cross section for the conductor. For small cross conductor, standard round wires are used. For large section, square or rectangular conductors are used. Once again, it depends upon the rating of machine. If you go for a small machine, you can go with round wires. If you go for higher rating machine, you can go with a rectangular or a square conductor. Okay, now calculate the winding height. So entire field winding will not done for entire pore length. Certain space will be left. So calculate the HF is nothing but height of the field winding. So HF is something but height of field winding is equal to what? HPL, height of the pole minus height of the shoe minus insulation and clearance. Okay, if you come back to the figure, this is what you called as a height or the field winding. So for entire pole, you're not going to mount the field winding. So this will be what? This will be the length or height of the field winding you are going to mount. So how do you calculate here? This will be what? This will be length of pole shoe, and this will be length of the pole, and between the field winding and between the field winding, we are going to leave for insulation. Okay, clearances you're going to leave that you can calculate. See here, HPL length of pole. What is the height of the shoe? 0.1 to 0.2 of HPL, height of the pole. Okay, height of the pole, 0.1 to 0.2 height of the pole minus 0.1 to 0.15 insulation and clearance. Okay, insulation and clearance. 0.1 to 0.15 of tau. Tau is something about pi d by p. Okay, this is for to find out the height of the field wind. Okay, this is a formula. Now once again, number of turns provided. This you can remember the formula. TF is equal to what? HF into TF divided by SF. What is HF? HF is nothing but height of the field coil. I go back to the figure here. HF is nothing but height of the field coil. DF is nothing but depth of the field coil. And SF, you got here SF. SF is nothing but a space factor for winding. Space factor for winding means nothing but you are going to take this surface area. This surface area you are going to take it. Let us see what regarding space factor. Where SF is nothing but a space factor, where SF is equal to space factor for the winding, and the space factor for round insulated conductor is 0.75 D by Di, where D and Di are diameter of bare and insulated conductor respectively. So 0.75 D is something about diameter of bare winding, and Da is something about diameter along with the insulation. And 0.75 into D by Da whole square, and that is called as your space factor for the winding. If you take entire thing, TF is equal to HF into DF divided by SF. This is what the formula for number of turns provided. And I check for current density in the shunt field winding. So current density is nothing but what? Your current by area, IF by AF. Okay. The value AF you can calculate. AF you can calculate with this formula. With this formula you can calculate AF. Okay. And then next, calculate the copper loss in each field winding. Copper loss. Okay. Next, okay here now. Okay. The value of current density in the shunt field winding would be around 1.2 to 2 ampere per mm square. In case of depth, suppose if you leave for a cooling purpose, it can go up to 3.5 ampere per mm square. And find the MMF provided. MMF nothing but what? A magnetic 40 force provided in the field winding, which is responsible for the creation and the flow of flux. ATF is nothing but what? IF into TF. That is nothing but MMF ampere turns, IF into TF. Calculate the copper loss in each field winding. Definitely QF is equal to what? Copper loss I square, IF square, RF. And cooling surface of each coil. Cooling surface of each coil S is equal to 2 LMT into AF plus DF. AF is the area, DF is depth, and 2 LMT is nothing but your length of printer. 2 LMT into AF plus DF. Temperature is in the coil, theta is nothing but your QF into C divided by S. Where C is something about your cooling coefficient given by the formula 0.14 to 0.16 divided by 1 plus 0.1 VA, where VA is something about the very fast speed of the armature. Okay, this is what to find out the temperature is in the coil. You are going to use this formula. Okay. Likewise, we have a design for field winding. These are the formula for design of field winding. So normally, not a single problem will ask from the design of field winding. So we will concentrate with respect to shunt field winding. So these are the procedure you have to follow. These are 12 procedure you have to follow to design the field winding, shunt field winding, a little bit lengthier one. And for each problem, based on the data given, you have to analyze and you have to solve it. So we have 5 standard problems in Ekesani. Same problem I'm going to take, and you practice those 5 problems correctly. Because out of that 5 problems, anyone they may ask for design of field winding. With this, try to solve one problem today. Another 4 problems we'll solve in the later classes. See here, we will solve one by one. The following particulars refer to a shunt field coil for 440 volt, 6-pole DC generator, MMF per pole, nothing but ampere turns, 7000 ampere, depth of the winding, DF, 50 mm, length of the inner turn, means LI, small LI, 1.1 meter, length of outer turn, L0, 1.4 meter, loss radiated from the outer surface excluding the ends, means loss radiated from the outer surface, means only from the outer surface. Because if there is a heating effect due to your winding, loss radiated from the outer surface only have to take it. Don't consider with respect to inner surface. They are given in the problem based on the condition they are given. You have to calculate the loss. In this problem, they ask what? Loss dissipated or radiated from the outer surface of the coil. That I have to take into consideration. Okay. That is one. It's given what? 1,400 watts per meter square. So per meter square, what will be loss? They are going to they are making assumption. It will be what? 1,400 watts per meter square. So you have to find the area. So you have to find the area of that your field winding, so that it may be what? It may be 2 meter square or it may be 10 meter square, and multiply with what? 1,400. Because 1,400 watts per meter square. For 1 meter square, it is 1,400. If area of your field winding comes around, for example, if I said 5 meter square, then 1,400 into 5. That will be the loss dissipated from the outer surface. Then once again, space factor 0.62. Space factor is something but your SF. Resistivity is something but rho. 0.02 ohm per meter and mm square. So resistivity is nothing but what? Rho L by A. Rho L by A. And this will be the unit. Rho per meter and mm square. Calculate. Based on this data, again calculate the diameter of the wire, diameter of your conductor of the field winding, length of the coil, nothing but your length of meter, number of turns, TF, exciting current, nothing but your IF. You're going to excite that field coil, you're going to calculate IF. Assume that voltage drop of 20% of terminal voltage across a field regulator. So there will be a drop of 20% due to loss, due to voltage drop. That comes from around 20%. So let us go step by step now. So what I have to calculate? These are the parameters we're going to calculate normally: diameter, length, number of turns, IF, then loss. If you see a loss, you can calculate the loss of. You go step by step. Voltage across shunt field winding. As in the problem given, there's a 20% drop. So what you take 0.8 into 400. So what is the 400 here? This is the 400 volt. So voltage across shunt field winding. So this voltage will be what? 252 volts. How many poles are given? They are given 6 poles. So for entire 6 pole, because all the poles are the shunt field windings are connected in series. So if we take entire 6 pole, then what is the voltage across shunt field winding? The voltage across the shunt field winding will be what? The total voltage across shunt field winding across it will be what? 352 volts. Because they given that 20% there will be a drop in the shunt field winding. Next, calculate what? Voltage across each field winding. What I want voltage across each field winding. EF is something but what? 352 divided by 6. 352 divided by 6. What you get now? 58.7 volt. So 58.7 volt corresponds to the voltage drop in each field winding. Means in a single pole. 57.7 volt. Next, find out length of the coil. First, second P, length of the coil. Length of the coil is nothing but what? Your length of meter. So take length of meter. Since here given what? They are given what? The length of outer turn they are given, the length of inner turn they are given. So LMT, the length of meter LMT is equal to L0 plus Li divided by 2. So 1 plus 4 plus 1.1 divided by 2, 1.25. So as I told earlier here, okay, this is nothing but what here. So they are given what? They are given inner turn and they are given outer turn. So you have to take average. So this dotted line represent what? This dotted line represent your LMT. Your ABCDEF GH is called as LMT. Length of meter. In the problem they already given L0 plus Li divided by 2, 1.25. That is first part, length of the coil. Let's calculate the diameter of the wire. So diameter of the wire, you can calculate here. Diameter of the wire. You first calculate area now. Now, area of the field conductor, AF is equal to what? Rho LMT TF by RF. Rho LMT TF divided by RF. Substitute for RF, EF by IF. This IF will go to the numerator. Rho LMT ATF by EF. AT by, okay, here. TF into IF is nothing but what? Your ampere turns. TF into IF is nothing but your ampere turns. EF is nothing but voltage available in a field winding for single pole, rho LMT. Substitute here, rho is equal to 0.02 into LMT 1.25 into ampere turns. Given the problem ampere turns, the total ampere turns of the pole, okay, per pole, it is 7,000 divided by EF. EF is something about what? 57.5. So here you can say rho is something but what? Ohm per meter into mm square. Ohm per meter into mm square. LMT will be in meter. So ohm per meter means the meter get cancelled. Remaining what you left with mm. You left with what? Mm square. Okay. So if you solve this one, what you get? 2.98 mm square. Okay. LMT will be in meter. Rho will be in what? Ohm per meter. Meter get cancels, and what you left with what? Left with your mm square. Okay. So the area of a field conductor will be what? 2.98 mm square. Once you find out the area, what AF is something but what? 2.98 mm square. Area is what AF is nothing but what? Area of here you are going to consider what you are going to consider a round wire and the circular conductor. Circular conductors, the formula for area pi r square So pi r square, what is r now? R can be written as what? D by 2, pi d square by 4 is equal to 2.98. And d square is equal to 2.9 into 4 divided by pi, you get 3.79. And diameter, if you take, what do you get diameter here? D is equal to 1.95 mm. This will be what? This will be to find out what diameter of the wire. So how do you want to find out diameter of the wire? First you calculate area. After the calculating of area, then you calculate the diameter. This is the second part of your answer for second part of your question. Next, say find out number of turns. Number of turns here. Total available area of the field winding. Here, just concentrate here. Total available area of field winding. HF into DF. This is HF. This is DF. Into SF. SF is something what you nothing but the surface in the problem it has given. It has given what? Space factor. Okay. HF into DF into this space factor. The space factor is something but what? SF is equal to what? 0.75 D by DI. D is something but diameter of wire conductor and DI is something but the diameter of the insulated wire. That is your SF. HF DF into SF. So the total available area of field winding. This is one formula. Also we have alternate formula to calculate the total winding area. So total winding area also equal to what? Area of field winding. Okay, area of field winding into number of turns. So area of field winding, you can take area of field winding into number of turns. That will be what? That what you get? You'll get the total winding area. Number of turns into area of field winding. If you take, you'll get total winding area. So TF into AF into 10 power minus 6 because mm square I'm converting into meter. Okay. Here AF what you got here? AF you got 2.98 mm square. I'm converting into meter 10 power minus 6. So these are the two formula available to calculate what? To calculate the total winding area. Total winding area. So now, I can write now what? Total winding area also equal to TF into AF into 10 power minus 6. So total winding area also given in the form of HF DF into SF. So substitute here with these two equations. You can substitute here HF DF into SF equal to TF into AF into 10 power minus 6. So from this you can always find out what? You can always find out TF. What is TF now? TF is equal to HF DF SF divided by AF into 10 power minus 6. Okay, HF DF SF into A into AF into 10 power minus 6. Try to substitute now. HF you don't know because HF height of the field coil we don't know what is that. Then depth is given. What is depth here? Depth of the field coil. You can see here. Okay, depth of the winding is what? 50 mm. Depth of the winding is nothing but this is depth of the winding. Okay, this is called what? Depth of the winding. Depth or thickness of the winding. Here, thickness of the winding, depth of the winding is nothing but 50 into 10 power minus 3. I'm converting into meter into SF. Surface factor means SF is nothing but space factor. SF is nothing but what? 0.75 D by DI. That is the formula for SF. But in the problem directly they give the value. SF is equal to 0.62 into AF. AF you already calculated AF here. 2.98. 2.98 into 10 power minus 6. Just do the calculation here. What I got here? 10.40 HF into 10 power 3. This is 10 power minus 3. If you take to numerator, it will come 10 power 6. So then what you get? 10 power 3. So TF is equal to 10.40 HF into 10 power 3. Take this as equation 1. Because if you want to calculate what? You want to calculate the number of turns. We don't know regarding HF. Try to calculate HF now. That is equation 1. Now, loss radiated from the outer surface excluding the ends means excluding ends. Here just concentrate here. Loss radiated from the outer surface excluding the ends means what you can say here. The loss radiated from the outer surface. How many surface you have? Outer surface excluding the ends. These are the outer surface. Okay, and this is something what? This is something what your length of meter of outer turn. This will be inner turn. This is the outer turn. Length of meter of outer turn. The loss dissipated or radiated from the surface. So what I can take? I can take length of outer turn into HF. I can take length of outer turn into HF because this is height into entire turn. If you take, then it will give what? Lot dissipated or radiated from the outer surface. This you remember here. Okay. So QF is equal to what? L0 into HF. I repeat once again. L0 is nothing but outer turn, length of midterm, of the outer turn of a field winding into HF. Okay. So L0 into HF. L0 is given the problem 1.4 into HF. So loss radiated from the outer surface of the excluding ends QF, or you can say at a permissible loss, QF is equal to now what you get here? You get 1.4 HF. But if you go to the problem, it has given it has been stated that the loss radiated from outer surface excluding the ends what 1400 per meter square. Means per meter square the loss will be around 1400 watts. So you have to calculate what is the area of this one. What will be area? Whether it will come 5 meters square, or it will come around 10 meters square, or it will come around 2 meters square. You have to calculate. Okay. Then whatever the area you get, multiply into 1400. That will be the total loss. Okay. So permissible loss 1400 per meter square. 1400 per meter square. What is the area you calculate now? 1.4 HF. 1.4 HF. So 1400 into 1.4 HF, because this is the loss radiated or dissipated from the outer surface. What you got? 1.4 HF. L0 into HF. So 1.4 HF, what you got here? 1960 HF. So permissible loss QF is equal to 1960 HF. Also you have a formula that power loss dissipated in the field winding. You can write it in this way. Q is equal to what? QF. QF is nothing but IF square RF. So IF square into RF can be done as what? EF by IF. So IF cancels, then what you get here? IF into EF. Then what you get? IF is equal to what? QF divided by EF. So come back here. Using this relation, IF is equal to what? QF by EF. What is QF now? QF is 1960 HF divided by EF. EF you got 58.7. Then what you got here? 33.4 HF. So field current HF is equal to what now? 33.4 HF. Now come here. Now ampere turns ATF. ATF can be written as what? Ampere turns. A stands for IF. T is nothing but number of turns. Ampere turns is nothing but what? IF into TF. Substitute for IF. What is IF here? IF is equal to 33.4 HF. 33.4 HF into TF. That's the equation. From this, you try to calculate what? Try to calculate TF. So TF is equal to what now? TF is equal to ATF divided by 33.4 HF. What is ATF? Is given the problem. Ampere turns per pole. If you go back to the problem, ampere turns per pole is what? 7,000 amperes. Okay, 7,000 amperes. 7,000 divided by what? 34.4 HF. So just calculate here. What do you get? 210 divided by HF. Do the calculation. 7,000 divided by 33.4. What do you get? 210 divided by HF. From this you calculate HF now. HF is equal to what? 210 by TF. This is equation 2. So we got equation 1 here. This is equation 1 and equation 2. Substituting for HF in equation 1. So take equation 1. Equation given as what? 10.40 HF into 10 power 3. 10 power 3 HF. Substitute for HF here. 210 by TF. So if you solve this equation, what you get now? You'll get TF square. TF square is equal to, multiply all those things, you'll get this number. And TF is equal to what? 1478 tons. Once you got, this is something but what? To calculate number of tons. TF is equal to 1478 tons. This is your third part of your problem, number of tons. Then still what you have to find out? Still you have to find out the current, exciting current, nothing but IF. Okay, we continue. Now, first calculate resistance of the field coil. RF is equal to what? Rho LMT TF by AF. TF, now you got it here, substitute all the things here, then what you got? RF. What is RF now? 12.4 ohms. Once you know RF, I can calculate what? I can calculate IF. IF is equal to EF by RF. 58.7 divided by 12.4 is equal to 4.73 amperes. So this is IF. If you want, you can calculate what? This is not as HF. You want to, you can calculate. Height of the coil, HF is equal to what? Take this equation and you calculate. HF is equal to 210 by TF. So this is the height of the coil, 0.142. So height of the coil is what? 0.142. Now you can calculate. Permissible loss QF is nothing but what? 1960 into HF. Permissible loss 1960 into HF. So 1960 into HF is equal to what now? 278.32. So total loss in the field winding for one pole, it is what? 278.32. So if you come back, this is the solution of the problem. If you come back here, what is the total area of the outer surface of the coil? 1.4 into HF. If you get, what is HF you got here? 0.14. So 0.14 means 1.4 into 0.14 if you take. So it will be less than a meter also. 1.4 into 0.14. If you take, it will come around 0.2 meter square. So 0.2 meter square. So what is the loss given the problem? It is 1400 watts per meter square. Since the area now area of the field winding is comes around only 0.2 meter square, definitely the total loss of your field winding will be what? 278.32 watts. Because the area of your field winding will be very less than a meter square, less than even meter square. Nothing but 0.2 meter square. That is why the loss coming around your field winding will be what? 278.32 watts. Okay. This is what this is the solution for the a shunt field coil has developed an MMF of 9000 amperes. A voltage drop in the coil is 40 volt, and the resistance of the round wire used is 0.21. The depth of the winding is 35 mm approximately, and length of meter is 1.4. The length of meter is already given. Design the coil. Design the coil means once again you have to calculate the exciting current, you have to calculate the number of turns, and then you have to calculate the diameter of the conductor. Other things you have to calculate. Design a coil so that the power dissipated is 700 watts per meter square. Means per meter square, the loss will be what? 700 watts. What is surface given? The total coil surface, outer, inner, top and bottom. Outer, inner, top and bottom, we have to consider all the surfaces now. Outer, this is the outer, inner means this is top, outer means top, bottom, and outer means this is outer. Outer all four sides. This is the top surface and this is the bottom surface. You have to consider all these surfaces. Inner means here. This is inner. This is inner inside here. Where we'll have a pole here inside. Around the pole you are going to own your shunt field coil. This inner, this is outer, this is top, and this is bottom. So they are told all the four surfaces. Okay. Inner, outer, top, and bottom. Take the diameter of insulated wire 0.2 mm greater than the bare conductor. So you have to design coil means you have to design the number of turns, you have to design what's the current and what is the loss. What is the loss QF you have to calculate. Along with that, you have to calculate the exciting current and the diameter of the conductor. You have to do it. Okay, let us do now. Area of field conductor AF, rho LMT TF by RF, same formula. Substitute here 0.021 into 1.4. LMT is given, length of meter is given here 1.4 into 9000 ampere divided by 40. So what you get here 6.62 mm square. Once you know area, then you can calculate what you can calculate diameter. Pi r square by d by 4 d 6.62 into 4 divided by 8.43. So d is equal to 2.90 mm. So diameter of bare conductor d is equal to 2.90 mm. But in the problem it has given what? Take the diameter of insulated wire. So you have to take insulated wire because for a bare conductor there will be insulation. Always there will be insulation before going to the winding. So diameter of the insulated conductor di, diameter of the insulated conductor di is equal to what now? 2.9 plus 0.2. So 0.2 is given. This point is nothing but your insulation around the bare conductor. 2.9 plus 0.2, 3.1 mm. Then calculate space factor. SF is equal to 0.75 d by di. I think this is whole square. This one 0.75 d by di whole square. I think I missed the whole square here. And just that the correction you make it. So I'll go to the design here. D by di whole square. Okay. Let's check that answer. D by di whole square. Okay. So 0.75 d by di whole square. So what you get here, space factor 0.66. I missed the square here, you put the square here. 2.9 divided by 3.1 whole square into 0.75. So 0.66. That is your space factor. Then total available winding, total available area of the field winding is nothing but HF dF into SF, Also, the total winding area also equal to TF AF into 10 power minus 6. Once again, you equate this to HF TF SF into TF AF into 10 power minus 6. Then what you calculate here? TF is equal to what? 3.5. Substitute all the value here. HF is not given. DF is there. Depth is given 35 mm. Converted into meter. SF is there 0.66. Substitute here. What you get here? 3.5 HF into 10 power minus 10 power 3. This is your equation 1. 10 power 3 means what? This is 10 power minus 6. Take to numerator 10 power minus 3. What you get here? 10 power 3. 3.5 HF into 10 power 3. Equation 1. Total dissipating area of the coil considering all the surfaces. Considering all the surfaces means what is the formula given here? 2 LMT HF plus DF. How you got that formula? See here. HF into DF. See here. 2 LMT. So this is nothing but what? The average, if you take this is the inner turn and this is the outer turn, in that you have average here. So LMT, this is LMT to LMT into DF plus for the bottom surface LMT into DF. So what you get here? 2 LMT DF. Likewise, for inner surface, this is inner surface here. This is the inner surface where we have a pole here. After the pole, you are going to place this winding. This is inner surface. For inner surface, once again, here inner surface. Once again, what you do? LMT into HF means your meter into HF. Then once again, for outer surface, LMT into HF. So what you got here? So you got 2 LMT into HF plus DF. 2 LMT HF, 2 LMT DF. So I have taken common 2 LMT. The remaining is what? HF plus DF. Okay. So 2 into LMT is given 1.4. HF is not given. Plus DF is given. I am counting into a meter. Putting in meter 0.035. 2.8 HF plus 0.098. Okay. That is what, this is what total winding area available where the losses takes place. Total winding area available where the losses takes place. Okay. Permissible loss QF is equal to what? 700 watts per meter square. 700 into this surface. What we calculate here? This surface. 700 into 2.8 HF plus 0.098. Okay, just you do the calculation here. 1960 HF plus 68.6 equation 2. Also, permissible loss is given by what? QF is equal to IF square into RF. IF square can be written as what? EF square by RF. RF cancel here. Then EF square by RF. Then you substitute for RF. Substitute for RF from the formula. RF is something but what? Rho LMT TF divided by AF. Substitute for RF. EF square AF divided by rho LMT TF. A normal formula is what? RF. Rho LMT TF divided by AF. So this AF come to numerator. So what will get QF? Then substitute these things. EF is something about 40 into AF calculate 6.62 and resistivity 0.021, LMT 1.4 TF. So just do the calculation here. What you get? This large value divided by TF. Equation 3. This is equation 3. From this equation 2, QF is equal to this term and also QF is equal to this term. So equate 213. If you equate 213, what you get here? 1960 HF plus 68.6 into this value. So you calculate for TF. So TF is equal to the entire large value divided by this term. Take that equation 4. Now what you do next one? Equating equation 1 and 4. This is equation 4 and you have equation 1 here. This is equation 1. Both are in terms of TF. Equating 1 and 4. If you equate 1 and 4, then what you get? You get 1 and 4. Then what you get? You get HF. Once you get HF what you get? Okay, 1 and 4. Then you can calculate for TF. Then you get 1 and 4 means in terms of HF you can calculate. So here in equation 1, TF is equal to 3.5 HF. So finally what you can calculate? You can calculate HF. Once you know HF, you can calculate TF. So TF is equal to how much now? 993 tons. Then finally you can calculate field current. IF is equal to QF by EF. So normal how you got this formula? I said earlier, QF is equal to IF square RF. From that I can get this formula. Nothing but power by voltage. Power by permissible loss by voltage. IF is equal to QF by EF. So what is the loss now? 363. 363 divided by 40. So this is EF nothing but 40. Then what is the field current here? 9.07. So permissible loss QF you can calculate here. Once you know TF, you can once you know TF you put it here. QF is equal to what? From this formula you can calculate what is QF here. Here QF. You can use any formula. You can use it, no problem. Either you can use this formula or this formula. What is QF here? QF is equal to this whole term divided by TF. TF I know. TF you put it here. So what I got? Permissible loss. What I got here? 363 watts. Okay, 363 watts. So field current you calculate QF by EF. So they are given what 700 watts per meter square. So what is the final loss I got for taking both top, bottom, inner and outer? What I got? Only 363 watts, because the area, this area is you calculate HF is equal to 0.15 meter. So you calculate here HF is equal to 0.15 and you do the calculation. Definitely it will be less than a meter. That is why what you got meter square, less than a meter square. So that is what we got here, lesser loss, around how much? 363 watts. Okay. If I calculate here 2.8 into 0.15 plus 0.098, definitely it will be less than a meter square. Okay. That is why what we got here, loss is equal to 363 watts, because the winding available area for the shunt field winding is very less. So loss also will be very less, even if we consider all the surfaces, top, bottom, inner and outer. Okay. This is what the solution for second problem. Okay. Let us hold this shunt generator with all field coils connected in series required an MMF of 5000 ampere per pole. The poles are rectangle dimension, it's nothing but 120 into 200 mm square, 120 width and 200 length. And the available cross section is 120 into 25 mm square. This I think I told in another way yesterday, just to rectify it. Winding cross section is 120 into 25 mm square. Determine the cross section area of the wire, the number of turns, and the dissipation watts per meter square based on the area of outside surface and two end surfaces. The conductor is round cross section used. The resistance is 0.002. And insulation of wire increased by diameter by 0.2. Allow a voltage drop of 50 volt in the field regulator. This is a statement of the problem. Since in this problem they are not given directly a length of meter, and then you have to calculate the length of meter. I'll just go through these things and I'll come back here. If it don't give a length of meter, whether it is a rectangular pole or whether it is a circular pole, just I'll run through here. So if you take a rectangular pole, the length of meter is nothing but what here? A, B, C, D, E, F, G, H. So once again, as you know, this is 2AB, 2CD, lengthwise 2CD, and we have once again TI plus 2 TI. In a similar ways, in lengthwise, what we got here, once again 2 LP, 2 lengthwise here, this length and this length, and 2 insulation here, this TI and TI, and what we got 4 BC. 4 BC is something but if you take if you consider this size something but what it's something but if you take a full circle, it's something but 1/4 of the circle, okay, quarter of the circle. So 4 into BC. So 4 into 4 parts here. 1, 2, 3, 4. 4 into BC. This is BC. BC is something but what? Nothing but an arc. If you take this BC into 4 times, it will become a circle. So this corresponds to a quarter of a circle. So what is the if you have a full circle, then what is the circumference? Pi into d or 2 pi r. If you have a half circle, what is circumference? Pi d by 2 or a 2 pi r by 2. If you have a quarter circle, it is something about what? Pi d by 4 or 2 pi r divided by 4. So BC is something but what? Pi d by 4. Pi d can be written as what? 2 pi r by 4. Here r is nothing but what? If this is a depth df, you can see it. This is a depth of the field winding. This is a depth, and length of meter is exactly at the center. So what will become this r? This arc will become df by 2. Now from the center point to this arc is nothing but what? Is nothing but radius. For this arc QR, these are all radius. So any point if you take from center and you join that outer part, it will become a radius. Even this part, these are all called as radius. So 2 pi r is equal to what now? Df by 2. 2 to get cancelled, 4 get cancelled. Then what you get? You get pi df. So if you solve this one, what you get here? Pi into dA plus 2ta plus df plus the 2 into LP plus BP plus 4ti plus pi df. This will be what? This will be in nothing but what? The formula for what? For length of meter. If they give the data regarding the width, length, and the thickness and df. This will be what the length of meter. Likewise, in if you take circular poles, if you take circular, this is length of meter. Length of meter is nothing but a circle. Circle can be written as what? Pi into d. This is a d. So I have to calculate this d. If I want to calculate this d, I should know what? I should know the diameter of the pole, then insulation, then this length. So d can be written as what? Pi into d. D can be written as di plus insulation of this part and this part insulation, and this df. The entire length is df. So I want only length of meter. So here it will be half df plus half df. Then what you get here? Full df. So pi into da plus 2ti plus df. This is for what? This is for if the poles are circular. If the poles are circular, this is the formula, length of meter. Likewise, if you want to calculate perimeter, this is a perimeter or outer turn. Once again, it remains here 2 LP plus BP plus 4ti plus 2 pi df. 2 pi df means if you take here, this is here, radius is nothing but what? Radius is nothing but df. So 2 pi r is equal to df. So 4 will cancel. What you get here? 2 pi df. So the external perimeter, I will be what now? It will be same. This will remain same for both length of meter or perimeter. Only what is the difference here? Here you got pi df. Here you got what? 2 pi df. So if you calculate length of meter, and you add another pi df, what you get? You will get the perimeter. Likewise, in circular, in case of a circular pole, what is the formula here? Same thing. Pi into da 2ti plus 2 df. So here. For this, I want L0. L0 is nothing but outer turn or your perimeter. So this is nothing but df. Here df plus here df. What you get here? Here 2df. Once again, this will be similar to what? Similar to this one. Okay. This will be LMT length of meter plus if you add pi df, then what you'll get? You'll get the outer turn. This is length of meter. If you know LMT plus what you can add? You can add this diameter. This diameter df. So pi into d. Length of LMT plus pi into df. If you add what you get the outer turn. Okay, that is the case. Okay, if they don't give L0 and Li, then this is the technique to calculate what length of meter. Okay, with this I will continue the problem. So here you have to calculate what? You have to calculate design. You have to design means you have to calculate number of turns, then what is the field current and what is the loss, all those things you have to calculate. Let us go one by one. Now here, the poles are rectangular in dimension. The poles are rectangular dimension means here 120 into 200 mm square. If you go back to the figure, yesterday I think I told regarding that figure, it is a rectangular. Rectangular means, okay, I'll show you. Rectangular, this is 120 and this is what? This is 200. And available winding area. Yesterday I think I did told in another way, but this is correct. The available area is given is what? 120 into 25 mm square. Available winding area 120 into 25 mm square. The larger value means the larger value 120 will go for height of the winding. The lesser value will be df. Means that is nothing but your 25. Okay. If you go back to the problem. Okay. If you go back to the problem here, see here. The available winding cross section is 120 into 25. 120 corresponds to what? HF. Come back here. 120 corresponds to HF and 25 corresponds to DF. And I think in previous class I had told it another way, but this is correct. 120 corresponds to HF and DF corresponds to 25. Because available winding area is something but what? Your DF into HF into what? Into this space factor. This is the available winding area. Okay. This is the problem given. And what you have to calculate? You have to calculate what the dissipation in watts per meter square based on the area of the outside surface and two in surface. Outside surface, so you have to calculate the power dissipated in outer surface and two in surface. Two in surface means the upper part, the top portion, and the bottom portion. That you have to calculate. Okay. Let us see. Let us let us solve the problem. Voltage across set field winding. Here in the problem you can see here it is given as 8 pole 500 volt. Means 500 volt is available across 8 pole. Let us calculate. And they are given that allow the voltage drop of 50 volt. And there is a 50 volt drop in the field winding. So voltage across shunt field winding. 500 minus 50, 450 volt. Voltage across each field coil. EF is equal to what? 450 divided by 8. What you get now? 56.25. Length of meter 2 into LP plus BP plus 4TA plus 5DF. 5DF. So 2 into 200, length is 200, width is 120, plus TA is not given, means this thickness is not given. This thickness is not given, so I want this LMT, so here thickness is not given, so I have taken as 0. 5 into DF, depth, as I told depth, the winding area available is something about 120 into 25. 25 corresponds to DF. So I get it here about 5 into 25. Then what I got LMT now? 0.72 meter. Next, find out the cross-sectional area of the wire. AF is equal to rho LMT ATF by EF. Substitute the values. ATF is 5000 ampere. What we got here? 1.34 mm square. Diameter of the wire AF is equal to 1.34 mm square by R square by D by 4. And D square is equal to 1.34 into 4 into 5, 1.75. D is equal to 130. So, a diameter of the base conductor is what? 1.30 mm. But in the problem, it has given insulation of what? 0.2. Diameter of insulated conductor DI is equal to what? 1.30 plus 0.2. It is nothing but what? 1.5 mm. Space factor 0.75 D by DI whole square is equal to 0.75. 1.30 divided by 1.5 whole square. What we got here? 0.56. So total available area for field winding. Total available area for field winding is nothing but the formula, the space factor into DF into HF. This is what the total space or total available winding area. Nothing but what? SF, HF into DF. SF is 0.56. Then HF, height of the winding is 120 and DF is 25. What you get here? 160.1680 mm square. Also the total winding area is also equal to area of the conductor into number of turns of field winding. TF into AF into 10 power minus 6. So equating what? You can equate this two term. Because you can equate this two term, then what you got here? If you equate, then if write for TF is equal to 1680 into 10 power minus 6 divided by 1.34 into 10 power minus 6. Then what you got number of turns? 1254 turns. After finding out TF, then find out resistance of each coil. RF is equal to rho LP by DF by AF. Then find out resistance. The shunt field current IF, EF by RF, 56.25 divided by 14.14, 3.97 amperes. Then find out what MMF required. ATF is nothing but IF into TF. IF you know here 3.97 into TF. TF what you got here 1254. So 3.97 into 1254, that is equal to 4978 amperes. So after finding out MMF required is something what you're going to cross check here. Already in the problem it has given 5000 amperes. Once you calculate IF and TF, you can cross check it. So it is almost equal to 5000 amperes. Now, dissipation in watts per meter square. This is what we're going to calculate. They have told in the problem that dissipation in watt per meter square based upon the area of outside surface and two end surface. Based on this condition, you have to calculate what? Calculate dissipation of power loss. Okay, dissipation, power loss due to dissipation. Okay. So if you come here, so what is the formula of dissipation in watts per meter square? Copper loss in the field winding divided by dissipation surface. Copper loss in field winding QF. QF is something but what? IF square RF. IF square you know, RF you know. Then this is 223 watts. This is due to the copper loss. What is the loss due to dissipation surface? Dissipating area outside surface and two end surface of the coil. Outside surface is nothing but what? Your L0. L0 into what? L0 into HF. L0 into HF. And two end surface, top surface and bottom surface. So LMT into top surface and LMT into bottom surface. What you got here? So LMT here. Okay. Two end surface. Two end surface means this part and this part. So LMT into your DF. Okay, this is the winding area. LMT into DF. because inner turn you have lesser length and outer turn you have greater length. So what you're going to take, you have to take the average value, LMT. So LMT into DF for top surface and LMT into DF for bottom surface, top and bottom. So what you got here, 2 LMT DF. Now I have to calculate what? I don't know LNT, L0. So what is L0 now? L0 is nothing but what? L0 is nothing but the outer turn. Outer turn are what we call as a perimeter. So once you calculate LMT, so the outer turn or a perimeter, directly you can use formula, or you already know LMT. LMT plus you add one more pi df. Then what you get? You get this outer turn. Okay, so length of outer turn L0 is nothing but what? LMT plus pi df. So you can see here. You already calculate LMT now. This is LMT already calculated. Then I want what? I want this distance. This distance is nothing but what? Once again, pi into df. So this is LMT. This already got LMT. Then for this arc you calculate pi into df. So what you get here? L0 is equal to LMT plus pi df. Otherwise, once again, if you want to calculate, you can go to that L0 is equal to what? 2 times LP plus PP plus 4 Ti into 2 pi df. Use that formula, then you can calculate. Otherwise, already you calculate LMT, then plus you add what? Pi df. That is the difference between your LMT and outer term. Only pi df is extra. So already I calculate LMT, you add pi df. So what you got L0 now? 0.80. Substitute here. 0.80 HF you got. HF is something but 120. I convert it into meter, 0.12. 2 LMT, 2 into 0.72 into df. df is 25 mm. Convert into meter, 0.025. So dissipating area outside the surface, what you got now? 0.32 meter square. Put in the formula, dissipation in watts per meter square. Copper loss in the field coil divided by dissipating surface. 223 divided by 0.132. Then what you got here? 176.15 watts per meter square. This is the solution for your third problem. In your last class I did it. Once again I have repeated. A little bit faster I have done. No problem. Let us go to fourth problem. See, all problems are different from each other, and these are the 5 important problems. I try to practice it. With these 5 problems, anyone can be asked the examination. Okay. Now, a 50 HP, 4-pole, 480 volt, 600 RPM shunt motor has wave-wound armature with 770 conductors. The leakage for the poles, 2 LES, 1 LES extra here, poles is 1.2. The poles are to be circular in cross section. The field coils are 70 mm thick. Field coils are 70 mm thick means directly it gives what? It gives the outer diameter, 70 mm thick, and produce an MMF of 10,000 ampere per pole. The flux density of the pole is 1.5 Weber per meter square. Calculate the diameter of the pole, diameter of the field wire, length of field coil, nothing but LMT, turns per pole, then field current. These are the parameters you should calculate. Keep 20% of voltage applied to the shunt field coil in reserve for speed control. Means nothing but 20% is used for to reserve for field control. Means out of this 480 voltage, you minus 20%. Assume that the thickness of insulation over the wire is 0.125 mm. Permissible loss is 1600 watts per meter square of the external surface. Of the external surface means same thing, L0 into HF. Resistivity of copper is 0.02 ohm per meter and mm square. A little bit lengthier problem. They asked diameter of the pole, diameter of the field wire, all those things they are asked. Let us calculate now. Diameter of the pole means if you see here, this is something put here. This is they are given what? Circular pole. If you see here, this is circular pole, and they are asked what? Diameter of the pole. Diameter of the pole, nothing but your DA or DP. After that you have insulation, you have inner turn, and you have outer turn. This is the scenario. The first what they ask what? Diameter of the pole. So for diameter of the pole, let us go step by step. Diameter of the pole. So if you want the diameter of the pole, we have a formula for diameter of the pole. Once you know area, because the poles are circular, if you calculate the area, then you can calculate the diameter. So here you have to calculate what? You have to calculate the area. AP is equal to what? Pi r square. Since the poles are circular, if you calculate the area, then I can calculate what? I can calculate the diameter. Similar to what you did for calculating the diameter of the conductor. Like in the same way, you have to calculate. So I want first what I have to calculate. I have to calculate AP. So yeah, everyone knows that flux density BP. Formula everyone knows that flux density in the pole is given by what? Flux by area. That formula I can use. Flux density is equal to what? Flux by area. From this formula I can calculate what? AP is equal to what? 5B by BP. So I have to calculate what? I have to calculate the 5P and I have to calculate dP. dP is given. Flux density of the pole is given. What is the flux density of the pole? 1.5 Weber per meter square. So what I have to calculate? I have to calculate the 5P. Means nothing but flux in the pole body I have to calculate. Flux in the pole body I have to calculate. Okay, let us calculate. So if we have seen the first class of the field design, I have given a certain formula there, leakage factor. Okay, definitely there will be a leakage factor even in the field coil. Leakage factor is nothing but what? Flux in the pole body divided by useful flux per pole. That is the formula. Okay, that things we are going to use it. Okay. Next year, if I want a flux in the pole body 5P is something but what? Leakage factor into useful flux per pole. Leakage factor is given the problem, it is something about 1.2. So what I have to calculate? I have to calculate useful flux per pole. If I calculate useful flux per pole, I can calculate flux in pole body 5P. Once I know 5P, I can calculate what? I can calculate area of the pole. Let us calculate now what? Useful flux per pole. For useful flux per pole, I want what? I want the what? EMF equation. Okay, EMF equation of your motor. Let us calculate speed now. Speed is equal to what? N is equal to N by 60, 10 RPS. Useful flux per pole. That EMF generated formula you don't know. That you know E is equal to what? 60 5 N by 5 N ZB by 60 A. That formula you can use. Okay. E is equal to 5 ZB and 5 ZNP by 60 A. So I want 5 is equal to what? E into 60 into A divided by ZNP. Z is equal to number of conductors, E is equal to EMF generated, N is equal to speed, P is equal to poles, and A is nothing but your number of parallel paths. So here, E into A. So what I have done here, 60 I have taken into numerator. Yeah, 60 I have taken into, denominator. 60 I have taken into denominator, N by 60. So N by 60 can be written what? N by 60 can be written as small n, means speed in RPS. Then you substitute here, E is equal to what now? 480. You calculate E is equal to 480 here. This is 480. The next step, A is equal to 2. So it is wave winding. You can see here the motor as wave winding. In wave winding, the number of parallel paths is equal to 2. So okay, that is 2 Z 770 conductors is given. 770 conductors into N. N is what? 10 RPS. We have calculated 10 RPS into 4. What the number of poles here? Number of poles is 4. So if you substitute here, then what you got? Useful flux 5. Nothing but 0.0311 Weber. Once you got a useful flux per pole, I can calculate what? I can calculate the flux in the pole body 5P. So flux in the pole body 5P is equal to 1.2 into 0.0311. So what you got here? 0.0373 Weber. Once you know 5P, I can calculate what? I can calculate the area of each pole body. Each pole body AP is equal to 5P by BP. 5P is 0.0373 divided by 1.5, 0.025 meters square. Once I know area, because it is circular pole, pi r square, pi dp means the inner diameter of circle, the diameter of the pole taken as dp, by dp square is equal to 0.025. dp means nothing but what? Diameter of the pole. So dp square is equal to 2.025 into 4 divided by pi. dp is nothing but what now? Diameter of the pole is nothing but 0.18 meter. So diameter of the pole is equal to 0.18 meter. That's the first part of your question. The answer for first part of your question, diameter of the pole. So for that you have to going to use this formula, and I think a BP will be given. So 5P you have to calculate. To calculate 5P, you record leakage factor into useful flux. So based on the data, you can calculate the diameter of the pole. That is first part. The next, what is second part? Diameter of the field wire and length of field coil. Let us calculate length of field coil now. Length of midterm. Length of midterm for circular pole, you know that pi is equal to di plus 2ti plus df. So they are not given regarding di, they are not regarding given df also. So what you have to do, let us see df whether they are given. Okay, df, okay. The poles are to be circular cross section, the field coils are 70 mm thick. Okay, depth is given 70 mm thick. Let us put it here. So di. So di means what? Dp is here. di is nothing but what? Length of inner turn. If you go to the pole, if this is pole, we know the pole diameter. Then after pole diameter, next to the diameter of the pole, you have some insulation. After that, there will be inner turn. Since regarding insulation, they are not given any value. So what I can do, DI can be written as what? DI nothing but what? Inner turn can similar to what? It is same as DP. Inner turn of your conductor wire, circular wire, is same as the diameter of the pole. DP, because DI they are not given. So DP plus 2 into 0, insulation is they are not given insulation here. 0 plus the DF is given, depth is given. See a depth is nothing but what? 0.07 meter. 0.07, 70 mm they are given, 0.07 meter. Convert into meter and calculate here. So what is the LMT now? LMT is equal to 0.785 meter. That is second part, answer for second part. Next, calculate diameter of the field coil. This is same diameter of the field coil. Here, if you see the problem, there's 20% voltage drop, because 20% voltage is applied to the is kept reserved for speed control. Means indirectly they are telling there's a 20% voltage drop. Okay. Now calculate now here. EF, voltage across each shunt field coil. EF is equal to what? 20% gone means remaining so much? Remaining only 0.8. 0.8 into 480 divided by P. So 0.8 into 480 divided by 4, 96 volt. So 96 volt is available across each shunt field coil. Area, AF is equal to rho LMT by TF by RF. Same thing you can do here, rho LMT ATF by EF. Substitute the value, rho 0.02, LMT calculated here, 785 into ATF is given 10,000 amperes divided by 86. What do you got here? 1.64 mm square. Once you know 1.65 mm square, always can calculate what? Always can calculate the T. T is equal to 1.45 mm. So, diameter of a bare conductor D is equal to what? 1.45 mm. Diameter of insulated conductor DI 1.45 plus 0.125. 0.125 is given the problem. This is nothing but insulation. You can see here. Here. Assume that the thickness of insulation over the wire is 0.125 mm. That is nothing but insulation. Okay, insulation. So diameter of the insulated conductor DI 1.45 plus 0.125. What you get here? 1.575 mm. Now, outer diameter of the field coil, required outer diameter of the field coil, thickness is given. Thickness is given what? Thickness DF is given. It's nothing but what? 0.07 meter or 70 mm. Thickness is given. So thickness here DF 0.07. Here if I put 0.07, then if you take entire length, that will be what? That will be your what? The outer diameter of the field coil. So inner is what? Inner is 0.18. What you got? 0.18 is nothing but what? Diameter of inductor or diameter of the pole. What you got here? 0.18. Plus, they are not given regarding the insulation thickness. Next, what you given? Depth 0.07. 0.07 for this side, and one more 0.07 for this side. 0.07. So outer diameter of field coil is nothing but what now? 0.32. Outer diameter of the field coil is now what? 0.32. So length of meter, outer diameter you know now, but what you have to calculate? You have to calculate length of meter. So length of meter, I can get out length of outer turn L0 is nothing but what? Directly can calculate is nothing but pi into D. Length of outer turn, pi into D. So pi into D, I can calculate here, pi into what is the D here? D is nothing but what? 0.32. L0 is equal to pi into D. Already got outer diameter. Okay. Okay, length of outer turn will be what? Pi into D. 0.32. Okay, and then what you got here? 1 meter. Once you calculate length of outer turn, then I can calculate the losses. Outer cylindrical, the loss is dissipated due to what? Due to the outer cylindrical surface. If this is a figure, this is what? This is nothing but your round pole, and this is nothing but your circular winding. So loss is dissipated in outer cylindrical surface. Cylindrical surface means this is your L0 into HF. That will be the surface where loss will be dissipated. So L0 into HF. So you can take here L0 into HF. Since L0 is 1, L0 is 1. So permissible loss. In the problem it is given that 1600 watts per meter square. 1600 into the available area. Available area is nothing but what? L0 into HF. L0 is 1. So 1600 into HF. That is permissible loss. Now let us calculate number of turns, and finally we'll calculate what? We'll calculate QF. So number of turns, field current IF is equal to QF by EF. How you got this formula? QF is nothing but what? IF square RF. From that you can get this formula. IF is equal to QF by EF. 1600. What is QF here? 1600 into HF by 96. So 16.7 into HF. Field MMF, ATF, substitute EF for IF. So 16.7 HF into TF. 67.1 HF into TF. What is ATF Q1? ATF is nothing but 10,000 amperes. So what is HFTF? HFTF is nothing but 599. So what is TF? 599 by HF. This is equation 1. And space factor is given. SF is equal to 0.75 D by DI or 0.75. D is nothing but bare conductor. Diameter of bare conductor, what we got? Diameter of bare conductor is how much? 1.45 mm divided by DI, insulated conductor. This is nothing but what? 1.75575. So 1.45 divided by 1.575 whole square, what you get is space factor. Space factor is nothing but 0.63. Total available area for field winding. Same thing, SF, HF into DF. So this is HF, this is DF. SF is nothing but space factor for circular conductor. Space factor, SF, HF into DF. 0.63, HF I don't know, into HF into DF I know, 0.07. Also total area of the winding also equal to TF into AF into 10 power minus 6. So I am converting into meter here. So equating these two, what I got? 0.0441 HF into TF into 1.64. AF is nothing but what? AF you calculated here for the conductor. AF. What do you got AF here? AF is 1.64. So 1.64 into 10 power minus 6. So what is TF now? TF is equal to 26,890.24 HF. This is equation 2. From equation 1 and 2, what is equation 1? This is TF. This is also TF. So equating equation 1 and 2, what you got now? This is equal to what? 590 by HF. What you got HF now? HF is equal to 0.15. Once you know HF, I can calculate what? I can calculate number of turns. TF is equal to what? 599 by HF. What you got number of turns? 3,993. So number of turns. So what you have calculated now? You have calculated number of turns. Finally, what you are left with? You are left with field current. So you can calculate field current. Then calculate resistance of field coil. RF is equal to rho L empty TF by AF. TF you know, AF you know, calculate 38.22. Then you calculate field current IF is equal to EF by RF, 2.51 ampere. Okay. This is what, this is the solution of this problem. Little bit lengthier, but you practice. Continue with problem number 5. Calculate the size of conductor and number of turns for a field coil of 6-pole, 460 volt DC shunt motor. The coil is to supply an MMF of 4000 amperes at working temperature. The length of inside turn is 0.74 meter, and length available for winding is 0.13 meter. The space factor for the winding is 0.52, and the permissible dissipation from the external surface, excluding the ends, is 1200 watts per meter square. Solution should not attempted by assuming a numerical value of winding depth. Resistivity of conductor is 0.02 ohm per meter mm square. Keep 15% of the applied voltage as reserved for speed control. This is the problem. So in this problem, we have to find what we have to find the size of the conductor. Nothing but you have to find out the area, and you have to find out what number of turns. Nothing but your TF you have to find out. And one condition is given in the problem is nothing but what you have to try to attempt to solve the problem without making assumption of the winding depth. Winding depth means nothing but your DF. So you should not assume DF. Try to calculate DF. And let us try to calculate AF or try to calculate DF. Okay. Let us solve the problem now. So voltage across shunt field winding equal to 1.85 into 460. Everyone knows that 50% of voltage is lost due to the power loss in the field winding, and nothing but high square or loss. Here, 50% of applied voltage as a reserve for speed control. Indirectly, that 50% is taken for other purposes, or nothing but you can consider it as a loss. So 0.85 into 460, what you got here, 390 volt. Voltage across each shunt field winding. So this 390 volt is nothing but what? Voltage across all the shunt field. We have 6-pole. So for 6-pole, 390 volts will be available. 390 volts will be available across the 6-pole. As you know that all the shunt field are connected in series. So voltage across each shunt field winding EF is equal to what? 390 by 6. So 65 volt. So 65 volt is available across each shunt field winding. Length of meter LMT. So you know that length of meter, if you want to calculate length of meter, means you have to calculate this A, B, C, D, E, F thing. So length of meter, everyone knows the formula. But here what they given, instead of giving length of meter, what they given, the length of inside turn. The length of inside turn is 74 meter. The length of inside turn means nothing but what they given, it is nothing but they given Li. This is Li. And this is your L0. L0 is nothing but a perimeter, nothing but your PQ, RS, RS, WX, Y, Z. This is your L0. And this is Li. After the insulation of the pole, this is your Li. So they given what? They given Li. But then you have to calculate what? You have to calculate. This. You have to calculate this LMT. You have to calculate LMT. So if they give Li, then you can calculate what? Length of meter. LMT is nothing but what? Li plus pi into df. Pi into df. If you come back here, so length of inner turn I know, plus what you have to calculate. You have to calculate what? This is nothing but what? This length will be same almost. All this width and breadth will be same. So at this arc, you have to put what? As I told earlier, if you combine all these four arcs, then it will become a circle. It's nothing but what? You can see this is nothing but a quarter of a circle. Likewise, if you combine all these four parts here, four edges, then it will become a complete circle. So length of mid turn is nothing but what? Li. Li is nothing but length of inner turn plus pi into df. So since here for length of mid turn, df is nothing but depth of the winding. This is df. Df is nothing but what? Depth of the winding. For length of mid turn, it will be what? It will be what? Df by 2. It will be what? Df by 2. So if you calculate, since if you join these four pieces, it will become a circle. So what is circumference for a circle is something but what? Pi into df. So length of meter will be what? Li, length of inner turn plus pi into df. So for this length of meter, what is the diameter here? Is nothing but what? Df by 2. Because this is df, this length of meter exactly will be at the half. So it will be what? Df by 2. If you come back to here, so length of meter LM is what? Li plus pi df. Li plus pi df. So this is nothing but what? This is nothing but a circumference. What is df now? Df can be written as what? 2r. Or you can written as what? Pi d can be written as 2r. So 2 pi r. So what is the radius here? What is the radius here? If you come back to the midterm, what is the radius here? This is radius nothing but what? Df by 2. So this can be written as pi df can be written as 2 pi r. R can be written as what? R can be written as df by 2. 2 get cancels. What is remaining now? Remaining is pi df. So length of meter LM2 is equal to Li plus pi df. Li is given 0.74 plus pi df. This is length of meter. Length of outer turn L0. Nothing but LMT plus pi df. If you come back to here, I want what? I want L0. L0 is nothing but what? A perimeter or PQRS WX YZ. This is your L0. I know length of mid-turn. Plus what I required. I required into pi df. So I can write what you can write here. L0 is equal to LMT plus pi df. Once again, d can be written as what? 2r or pi d or 2 pi r. What is r here? R is nothing but what here? R is nothing but what? R is nothing but here. You can see here. Radius is nothing but here df. Because I want the outer turn. This is nothing but df. So this can be written as what? Pi df can be written as what? 2 pi r, and r is equal to df. So length of outer turn L0 is equal to 0.74 plus 2 pi df. Okay, that is your length of outer turn. Now external reciprocating surface of each coil is equal to what? L0 into HF. So in the problem, if we go back to the problem, you can see here that the permissible dissipation of the external surface excluding the ends. That means the dissipation is taking place with respect to the outer surface, excluding the ends. If you go back to the figure, if this is a figure, this is called as outer surface. Or this fourth surface is called outer surface. Excluding the ends means what? You have to exclude the top surface and you have to exclude the bottom surface. How do you calculate? L0. This is L0 into HF. Okay, L0 into HF. So external dissipating surface of each coil S is equal to what? L0 into HF. L0 is 0.74 plus 2 pi df. 2 pi df into hf. 0.74 plus 2 pi df into hf, HF, 0.13. Is given the problem, the length of available winding. The length of available winding is what? 0.3. The length means nothing but your winding length. Winding length. At what height you are going to do the winding. It is given as what? 0.13. So HF is 0.13. It is given the problem. 0.13. So 0.0962 plus 0.82 dm. Take this as equation 1. Loss dissipated in the problem is given 1200 watts per meter square. So per area, okay, 1200 watts per meter square. So whatever the winding area available, you have to multiply with what? We have to multiply with 1200. So loss dissipated QF is nothing but what? 1200 into dissipation into the surface left for into the dissipating surface or loss dissipating surface. It's nothing but what? External dissipating surface is given by what? 0.09262 plus 0.82 dm. This is the area where the loss will be dissipated. So if you multiply with 1200 into 1200, then what you'll get? You'll get the loss dissipated surface. If because in the problem it is given as what? 1200 watts per meter square. Per meter square it is 1200. So this is will be what? The area of loss dissipation. You have to multiply with 1200. If you multiply with 1200, what you get here? 115 plus 115.44 plus 984 df. This is equation 2. And also loss dissipated QF is given by what? IF square RF. IF square substitute for RF, rho L empty TF by AF. Then just rearrange this term here. Rearrange this term. So what you got here? IF into IF. Okay. IF square. We make it IF into IF. So IF into TF is nothing but ampere turns, rho L empty by AF. So IF by AF substitute here. Ampere turns is given as what? Ampere turns is given as 400. Okay, this is 4000. Ampere turns is 4000. Just make the correction here. This is 4000. Ampere turns is 4000 into O is 0.02 into 0.74 into YDF. So you substitute here I by AF 59.2 plus 251.32 TF. Just make a correction here. It is not 400. It is 4000. 1 0 is missing here. Just make a correction. IF by IF 59.2 plus 251.32 df. This is equation 3. Total available area for the field winding. Total available area for the field winding is nothing but what? Your space factor SF into DF into HF. So space factor SF into DF into HF is nothing but what? Total available winding area. Total available winding area SF into HF into DF. Space factor is given 0.52. Height is given 0.13. DF you do know. So DF. So what you get here? 0.0676 DF. Total winding area also equal to what? Number of turns into area AF. TF into AF into 10 power minus 6. 10 power minus 6 nothing but I converting into meter. TF into AF. So since these two are related with what? Related with the total available area of field winding. So equating these two, what do you get here? 0.0676 DF equal to what? TF AF into 10 power minus 6. Then find out for TF. TF is equal to 0.0676 DF divided by AF into 10 power minus 6. This is equation 4. Now, substituting for AF in equation 3. Substitute for AF here in equation 3. So AF is equal to what? Substitute for AF. QF is equal to 59.2 plus 251.32 DF into IF divided by entire thing substitute for AF. Okay, substitute for AF. Then TF will go to numerator. So 59.2 plus 251.32 DF, IF DF divided by 0.067 DF into 10 power. Okay, into 10 power. This you take to numerator. It will become 10 power 6. Okay. 10 power 6. This will take to your numerator here. It will become out 10 power 6. So KF is equal to entire this term into what? Into IF into what? Entire this term. Then what you get here? Ampere turns. IF into TF is nothing but what? Your ampere turns. What is given here? 4000. Okay. KF is equal to 4000. Just solve this equation here. Then what you get here? 3.53 plus 15 df divided by df. This is equation 5. Equation 5, QF is equal to what now? This term. Also QF in equation 2. What you got here? This term. So equating 2 and 5. Equating 2 and 5. So what you get here? If you get equating 2 and 5, what you can calculate? You can calculate df. Just solve this equation. You'll get it in quadratic equation and calculate for df. So what you got df here? Df is equal to 0.027 meter or 27.6 mm. So depth of the winding you calculate now. What is the depth of the winding? 27.6 mm. Once you know depth of the winding, you can calculate always what? You can calculate always the loss dissipated. What is loss dissipated here? You have a formula there, 1200 watt per meter square into the surface available for dissipation. Okay, 1200. What you get here? 115.44 plus 984 df. Substitute for df there. If you substitute for df, what you get here? What is the loss dissipated? So 142.35 watts. So total loss dissipated. Total loss dissipated for available winding area is for how much? 142.35 watts. But in the problem it is given that what? 1200 watts per meter square. Per meter square it is 1200. If you see this loss dissipation, definitely the available winding area for loss dissipation is very less, even less than meter square. Once you calculate QF, then you can calculate what? You can calculate your LMT. LMT is equal to what? 0.70 plus pi into what you got here? If you go to LMT equation, you can get pi into df. That for df you substitute. What is df here? Df is nothing but what? 27.6 mm. If you say substitute for 27.6 mm, 27.6 mm convert into meter here. So it will become what? 0.0276. So what you got LMT now? LMT is equal to 0.082. Once you find LMT, always you can calculate what? Always you can calculate area of the field conductor. Area of the field conductor or dimension of the conductor. Area of the field conductor A is equal to rho L into TF divided by RF. Rho L into TF, EF by IF. RF can return what? EF by IF. IF go to numerator. Rho L empty. IF into TF is nothing but your ampere times 4000. EF is 65. Then if you calculate what you get AF is equal to 1 mm squared. So once you calculate AF, then you can calculate what TF. TF is equal to 0.0676 DF divided by AF into 10 power minus 6. You substitute and calculate. AF is nothing but what here? 1 mm square convert into meter. So finally what you got TF? TF is equal to 1866 tons. This is what a solution for a fifth problem, very much important problem. And this problem has several types. This is a solution for a fifth problem, where the LMT will be not given, you have to calculate the LMT. With this, we have concluded all the 5 problems based on the field design. All 5 problems are very much important one, and just go through and practice it. Okay, with this, I'll end my lecture. Thank you.